Hello everyone and welcome back to the channel. In this video we are going to discuss the fifth practice problem on linked list, and the question that we are discussing today is Leetcode question number 61, rotate list. So the problem statement mentions that given the head of a linked list, rotate the list to the right by k places. So you might have seen this problem in arrays as well, where we need to shift each number or each element in the array by k places. So how do we solve this problem in arrays? In arrays, we find the new index by doing current index plus k mod size of the array. So by using this formula, we calculate the new index from the present index and shift the elements using DFS or a helper array. Now in linked list, it is much easier to solve this problem. Let's try to check few examples and come up with a logic. Now to understand this problem, we'll be breaking down this problem into a few cases. So let's say that the size of list is n and we need to shift the elements by k. So case 1 is when n is equal to k. So let's look at this case when n is equal to k. So let's say that this is a list. One, two, three, and let's say that we need to rotate it 3 times. So n equal to k equal to 3. So after first rotation, the list will look something like this. 3 will move to the front, and so 3 will move to front. It will start pointing 1 and 2 will be at the end. In the next step, 2 will move to the front and all the other elements will move towards right by 1 place. So the list will look something like this. 2 will point 3, 3 will point 1, and 1 will be pointing to null. In the last step, what will happen? 1 will move to the front and all other elements will move to the right by 1 place. So the list will look something like this. So now we can see that the original list and the rotated list are exactly identical. Now we can try it for different n and k values, like we can try for n equal to k equal to 4 or 5, 6, 7. We'll see that after completing all the rotations, the list will always go back to its original form when n is equal to k. So now if we have a linked list of size n and we rotate it n times, so what will happen in the first time? The end node will go to the start, and every time in each step it will keep moving towards right by 1 step. So after n steps, what will happen? It will reach its original state, and same applies for all the nodes in the list. So after n steps, all the nodes will reach to their original place. So we can easily say that when k is equal to the size, we don't have to do anything. We can return the original list because the original list would not change at all. So not just for this case, this is actually true when k is a multiple of size. So for any k which is a multiple of size, after k rotations, we will get back the original list. And why is that? Let's say that k is n into size. And let's assume that size, just for the ease of understanding, size is equal to m. So we can say that k is equal to n into m. So after first m rotations, we know that the list will move back to its original state. So now we have to rotate it n minus 1 into m times. After m more rotations, it will again go back to its original state. So now we have to rotate it n minus 2 into m times. And we will see that after every set of m rotations, the list goes back to its original state. Now let's try to understand the next case, which is when k is less than n, or k is less than size of the linked list. So let's take another example to understand this case. Let's say that this is our linked list and here k is equal to 2. Now after first rotation, our list will look something like this. So 5 will move to the front and all other elements will move 1 step towards right. In the second step, 4 will move to the front and all other elements move towards right by one step. So this is our list. We can clearly see that rotating list twice is equivalent to breaking the list from the second last element, that is second last element is this element, breaking the list from here and moving the remaining list, which is 4 and 5, to front. So if we break the list from here and move 4 and 5 to front, what we get is the final list. Let's try to see if this can be generalized. Let's say that k is equal to 3 and the original list, let's take the same list, 2 3 4 5. Now the list looks something like this after 2 steps. If we give it a third rotation, the list would look something like this. 3 would come to the front and all other nodes will move towards right by one step again. So rotating the list 3 times is again equivalent to breaking the list from the third last element or the third last node and bringing the remaining list to the front. So if we break the list from the third last node and bring the remaining list to the front, what we'll get is the final result which we wanted. So every time when k is less than size and we need to rotate the list k times, so what we need to do is simply we need to find the kth element from back. From the end, we need to find the kth element, break the list from there and bring the remaining list in the start. So by doing this, we'll actually rotate the list k times. So the only case that is left is when k is greater than the size of the list. So let's assume that k is equal to 10 and size of the list is equal to 4. Now we already know that if size of the list is 4 and we rotate it 4 times, then we go back to its original state. So now size of the list is 4. For first 4 rotations, we will get the original list. Now we are left with 6 rotations. In these 6 rotations as well, if we do another 4 rotations, we'll again get the original list. So now we are left with 2 rotations. And when we are left with just 2 rotations, we have actually reached the second case. So this is the case when k is less than the size of the list. So by this we can infer that every time we have been given a value k and the size of the list is m, we actually need to rotate the list k mod m times. We do not actually have to rotate it k times, we just have to rotate it k mod m times. This is because for the first time rotation, the list will reach to its original state. For the next time rotation, the list will reach to its original state, and this will happen k by m times. And we are only left in the end with k mod m rotations, and this reduces the problem to the second case that we have already discussed. So now that we have understood the logic for the problem, let's quickly go through the code. So here, first of all, what we have done, we have defined a variable size because we need to first find the size of the linked list, and our whole logic is based on size, and size for a linked list is not pre-calculated. So we'll use this variable to store the size, and we also have two variables, two helper pointers, which we'll use for our logic. So one is travel. So the travel pointer will be used for traversing the linked list, and we also have a last pointer. So last here is going to store the address for the whole linked list, or it is going to store the tail of the linked list. So why do we need to actually store the tail or the last node of the linked list? So let's take an example that, let's say this is the original linked list and we need to break it from here, and we want to bring this remaining linked list in the front. So how do we actually bring this remaining linked list in the front? One simple thing that we need to do is that our last node of the linked list should start pointing to the first node. If we remove this reference, this particular reference, and our last node starts pointing to the first node, we'll actually bring this remaining linked list to the front. So that's why we have kept a helper variable or helper pointer last, which is going to store this tail that will help us in moving this linked list towards the front. So what we have done, we have a simple loop where we are actually traversing the whole linked list, and every time we are updating our last pointer because we want to reach the last node, and every step we are also increasing the size by 1. Now the first sanity check is that if size is equal to 0, we return null. If size is equal to 0, head is already null, then we do not have to do anything and we return null. Second is we calculate the actual value of k, or the actual rotations that we need to do. So we have already discussed that essentially we need to rotate a list k mod size times, because if k is less than equal to size, we simply know what we need to do. But when k is greater than size, so we just have to rotate it k mod size times. All the other times the list will reach to its original state. So we have calculated the pivot, or the number of rotations. Now if the number of rotations is, or pivot is 0, so pivot will be 0 when k is a multiple of size. So we have already discussed, when k is a multiple of size, then the list will reach to its original state after all the rotations. So we simply return head, we do not make any modifications to our linked list. But in the case if linked list is but in the case when pivot is not 0 and we have to actually break this linked list, so we calculate the index of the node from where we need to break. So we already know that for k rotations, we actually need to break the bond between k minus 1 and kth element from the back. So now what we are trying, since we have the total size and we know that we want the index of the kth element from the back, we can actually calculate its index from the front. So that is why we have actually calculated the pivot position from front, which is simply but size minus pivot plus 1. Now we are going to reach the element that we need. So by using a simple for loop that starts at 1 and goes till the index, we are going to reach that index. And now once we have reached this index, which is essentially this element, once we have reached this node, what we need to simply do is that we need to change the value of the next attribute in this node as null, because this node should not point to anything. This will be the end of the linked list now, and we simply need to change the value in the next attribute of the last node, because it should start pointing to the first node now. So by doing these two operations, we'll actually move this remaining list to the front. So we have done exactly those two steps. So our last starts pointing to the head, and the node that we have reached currently, we change its next to null. And what is the new head for the list? What is the new head for the list? When we will bring this list and put it in the front, the new head for the list is going to be this node, or the kth node from behind. So we simply take out the kth node from behind, or which is going to be the next node for our travel pointer, and we simply return that head in the end. Now, what is the time complexity for the solution? Time complexity is big O of n, because again we are traversing the whole linked list and it's a linear traversal, so it has a linear time complexity. And the space complexity is big O of 1, because we are just using constant helper pointers. We are not using any extra space as such, so that's why big O of constant or big O of 1. So I hope you understood the logic and the code for this problem. And in case you still have any queries or you were not able to understand something, please do mention in the comment section and I'll try to clarify it there itself. I guess we can end this video here. See you in the next video. Thanks for watching. Bye bye.